Okay, so everything looking good on the screen?
Yes, perfect.
Oh, there's always a first time. Okay, so I'm going to give a presentation talking about how to get the compilers to optimize for the processor in Ookami. And that's the Japanese symbol for Ookami at the top, in case you're wondering. So I'm doing this as a kind of public service announcement. It's a walkthrough of some of the info that's in the Ookami FAQ online already. The issue with FAQs, having been in charge of them before, is that sometimes you know what you want in there and you know what's in there, but other people don't. So I thought I'd just do a walkthrough of this, and then we can sort of see in real time what the tricks are to tell the compilers to do interesting things. So I think Ava mentioned the meat of the processor speed comes from vectorized operations, and the vector extensions on the A64FX are called SVE for scalar vector extension. And I should point out, I'm talking about C, C++, and Fortran, i.e. the usual suspects in high performance computing. So I'm not talking about Python or Rust or anything like that. Okay, so I thought I'd throw in a quick picture of the topology of the chip. So Ava also noted the distinction between the 1000 and the 700 chips between Fugaku and Ookami. So the Ookami processors have 4 NUMA nodes within each processor, which are called core management groups in the A64FX terminology, each of which has 8 gigabytes of RAM attached to the node and 12 cores within the group. All the cores in the different groups are then connected on a ring with a network on chip, and that's how they communicate with each other in the chip. And on our machine, on Ookami, there's also a local disk for the operating system. Because there's so little memory available on the node, having the operating system in memory didn't work out well, so we got disks for the nodes. And unlike Fugaku, which has the proprietary tofu interconnect, we have the usual Mellanox style InfiniBand. All right, so the issue in all the compiler stuff is how do you make best advantage of that architecture. So I'm going to jump straight in the interest of time, to going through the compilers that were mentioned earlier. So I'll start with the GNU compilers because that's the ones that everyone knows. So the term, if you weren't aware of this, the term GCC is often thought of as meaning that the GNU C compiler. That's originally true, but as more languages got added, C++, Fortran, and others, it now stands for the GNU compiler collection. So yes, GCC is the C compiler, but it's also part of a bigger family. And GCC has added vectorization support for the A64FX on version 10 something onwards. So we have installed in these modules versions of releases of the 10 dot something and 11 dot something, and the latest is 11.2. So if you're looking to get the performance, you want to make sure you use one of these newer GCC versions. And there'll be some examples coming up too of each of them. ARM. The architecture of the A64FX is an ARM chip, and ARM produced their own compilers. It's a fork of the LLVM framework. So if you're familiar with Clang and Clang++, this is an ARM extension to that, mainly by adding the word ARM in front of the compiler name, which is rather cunning. And ARM have added their own vectorization support to this fork of LLVM. And it also has this optimized math library called ARMPL that can get your speed up. You might have noticed that the Clang LLVM compiler was not listed earlier, and that's because it currently, in the released versions, does not support SVE. ARM, however, are upstreaming their changes to it, and I'm assuming probably release 14, it'll be there because you can see it in GitHub already. John might be able to expand on that a bit later. So the system came from Cray, as we just heard, which got bought by HPE, Hewlett Packard Enterprise recently. This is a very well-known compiler chain, especially in high-performance computing. And there's two versions available, one that has SVE support and one that doesn't, which is basically a rebrand of LLVM. So we're obviously interested in the SVE support one for our purposes for doing high-performance computing. And this also has its own optimized math library and other goodies too. Fujitsu is the vendor of the chip. They have their own compiler that's been around a long time, going back to K computer and before. It has good optimization of A64FX. You have to be careful for threaded programs though, and I have a link later on to the important information in our FAQ. This also has its own scientific library for optimized math, and it also provides an implementation of MPI based on OpenMPI, but with a number of changes made to it. I'm not going to talk about this too much. The Nvidia, used to be PGI compilers, for those of us who have been around a long time, is available for both the architectures in Ookami. There's no vectorization support at present. I tried it yesterday and with the latest version, and I didn't see any support. So I'm not going to say any more about that. So doing okay for time, I think. So summary. So there in the FAQ is a matrix of the compilers we have and the important options that help you get performance, or things that you should try to get performance. There are also flags for the various compilers that tell you what they're up to when they're compiling. So I'm going to have an example of this coming up in a moment. All right, so for GNU, as you can see, you load up the latest version, for example, and you can see in the second line that I have a program that's doing some kind of calculation loop, uses OpenMP, and I'm telling it to compile explicitly for the A64FX processor. So if you use this handy command, the Z or Z registers are the ones that indicate that SVE instructions are being used. And you can see here all the instructions. I'm not going to go through them. It probably looks like gibberish to most people, but this is indeed vector instructions. And I want to point out that, yes, this math library thing. So for GNU, you need to tell this to use the math library for the functions that I'm using in the code. We'll see in a moment that other compilers don't need that and substitute better versions. So for the ARM compilers, you load up the appropriate module, and the compile line looks almost identical to the GNU one. The flags are almost identical, which is nice for compatibility, except here I'm adding -RMPL, which needs to go both in the compile and the link commands, which is just collapsed into one here. So I don't need the -LM on the end to get the optimized math functions. And you can see this has got different vector instructions, but it is generating vector instructions. For the Cray compilers, you load up the latest Cray environment, and you can see here that the flags look completely different. And here I'm also telling the compiler, as well as generating really optimized and vectorized code, I'm also asking it to print out messages. And as you can see here, it does loop unrolling. So instead of going around in steps of 1, it expands the loop out into groups of 4, so that you go around the loop fewer times and improves the cache usage. And it also tells me that the loop was vectorized. So I then do my handy trick, and I can see that, yes, there are, in fact, vector operations here. There's the FMLA, for example, is the fuse multiply add operation. So that's the A times B plus C collapsed into a single hardware instruction, which is a common pattern in scientific code, of course. And for the Fujitsu, yet different flags. Kind of look they're sort of like the same-ish, but they use different letters. And again, I'm telling it explicitly to compile for SVE, and I'm asking it to use the SSL2 library, so I don't need -LM to get math, unoptimized math instructions. And again, you can see that it's using vector instructions with the Z registers. And please note this link at the bottom. So I'm using OpenMP here, so it's a thread parallel. And if you're writing code that's threaded in any shape or form, and especially if it crosses the CMG or NUMA node boundaries, please make sure you go and look at that link, because following the instructions there can turn your performance from awful to amazing. So to wrap up, so which compiler should you use? We don't know of a magic bullet, unfortunately. We're all trying to learn as we go along and find out more and more. And we've learned some things, and we try to document those in the FAQ. And while Fujitsu and Cray often produce really good code, they don't always play well with things like CMake and AutoConf, which I don't know about you, but for me is like 99% of the code I work with. So ARM and GCC have flags that play nicely with AutoConf and CMake. And I think it's really just a matter of trying to get CMake and AutoConf setups to evolve to understand those compilers. And so if you've got questions, I'm just repeating what Ava said, just to ram it home. We have the office hours twice a week. There's a Slack channel for asking questions. The trouble ticket system, as she said, is for technical issues like logging in problems and that kind of thing, or accounts. If you want science, higher level opinions and ideas on about how to get performance and profile things and debug and use MPI or OpenMP, these are the places to do it. And it's all documented on the web on that URL at the bottom. And that's me, done.